This video is an introduction to confidence intervals, and so we're going to start off here by trying to determine why we need to talk about confidence intervals. So to start off here, we know that up to this point we've used point estimates to try and estimate population parameters. So suppose we want to estimate a population mean, we would use a sample mean to do that. Okay. The point estimate that we've tried to use to estimate a population mean mu is the sample mean x bar. And we've done this for proportions also. So to estimate the population proportion p, we've used the sample proportion p prime. So in general, if we think to cases of trying to find a population mean by estimating with a sample mean, we want to know, is it likely that x bar is going to be exactly equal to mu? And the answer there is no. Okay, so most of the time we're going to expect our sample mean x bar to be close to mu, but it's not likely going to be exactly equal to mu. And keep in mind that x bar is a variable, so depending on which sample we take, we'll get a slightly different estimate of mu. So what we're going to do this time is we're going to look at using a better technique for estimating a population mean. And that is, instead of just using the point estimate x bar, we're going to create a confidence interval. So an interval around the value that we think contains mu. Okay. So basically we're going to use our best guess of the true population mean by using the sample mean, but then we're going to create an interval of values around that sample mean. And so the general process here is we're going to get our point estimate for mu, which is x bar, and then we're both going to add and subtract some quantity. We're going to call that the margin of error, and that's going to create an interval estimate instead of a point estimate. Okay. Another just term here as we go is that the margin of error for a confidence interval for a population mean is frequently called the error bound mean, or EBM. Okay, and so I've just got a visual here. We've got a distribution here, and this is the distribution of the sample mean x bar, and we know that the mean of all possible sample means is going to be centered at mu. But we know that there's some variability there, and so maybe I would take a sample mean and I might get, maybe I get this value of x bar as my sample mean. What you can tell is that x bar is not exactly equal to mu, so I've missed it. But what we are going to start looking at here is, instead of just using x bar to approximate mu, we're going to create an interval around x bar by both adding and then subtracting this margin of error up here to that x bar value, and that's going to create an interval, and we're going to be able to state how confident we are that that interval actually contains mu, the true population mean. And so what I've done below here, just so you guys can get a visual, is I've just created a whole bunch of possible confidence intervals around mu. Now normally these would be up here on the distribution itself, but I just, for visual sake, so that you could see a bunch of them, I'm just showing you. So maybe we got a sample mean right here, x bar, and we would create that interval. Maybe our sample mean was here and we created that interval. So these are all different possible sample means that we might create, and their resulting intervals. And what you can see is that even though x bar most of the time is not perfectly equal to mu, most of these intervals do capture mu somewhere within the interval. You'll notice this one doesn't, right? This one missed. And so sometimes that's going to happen, but in general, we're going to be pretty confident that we can create an interval that does contain the true population mean mu. Okay. So what we're going to take a look at on the next page here is just a little more background, and then we'll do an example. So you can see here that it says we just looked at 12 possible confidence intervals for a population mean mu. Each of those intervals was slightly different. Some contained mu, others didn't. I showed you one that didn't contain mu. And then here's some important information that says in reality, we're only going to create one interval based on our one sample mean from our sample data. And there's no way of knowing for certain if our interval is one of the ones that captures mu or happens to be one of the few that misses. Okay, so another piece of information before we go on to a kind of an overview example is if we have a 95% confidence interval, that's going to tell us that 95% of all possible samples of that given sample size will result in a confidence interval that contains or captures the true value of mu, and only 5% of the possible samples will yield an interval that does not contain mu. So if we go back to this page, what we're saying is if we ended up doing doing a 95% confidence level, if we created 100 of these possible sample means and their intervals, 95 of those would capture the true population mean and 5 of them would miss. Okay. So we're going to go on to an example where we kind of get an idea here of what we're talking about. So this says we have a sample of 32 small bags of candy. The weights are known to follow a normal distribution with standard deviation 0.1 ounces. And it says the mean weight of the 32 bags was 2 ounces. And we're supposed to approximate a 95% confidence interval for the population mean weight of all such bags, based on what we know about the distribution of sample means for samples of size 32. Okay. So basically what we're given here is that if we look at the distribution of X bar, so the distribution of all possible sample means for a given sample size, we know that if we want a middle area of 95%, right, or we want to be about 95% sure that that we create an interval that captures our population mean weight. We know from the empirical rule that means we are about 2 standard deviations above and below the mean. Okay, and so what we're going to do is we're going to take our sample mean, X bar, which we said is our best guess for our population mean mu. But we know it's wrong. We know it's our best guess, but we know it's wrong. And so we're going to both add and subtract 2 standard deviations above and below that mean. And why 2 standard deviations? Well, again, we want it to be about 95% sure. So we want 95% of the area to be in the middle and those 2 equal outer tails. That puts us at about 2 standard deviations above and below the mean. Okay. So the standard deviation of the sample mean X bar, just as a reminder, sigma sub X bar is equal to the standard deviation of X over the square root of n. Okay, and so what this becomes, and that was back from chapter 7, so this is X bar, back from chapter 6. X bar plus or minus 2 copies of that standard deviation. Okay, so our sample mean here for this problem, if we go back up, it says the mean weight of the 32 bags was 2 ounces. So there's my 2 ounces plus or minus 2 copies of the standard deviation of X bar, which was the original standard deviation, 0.1, over the square root of my sample size, which was 32. That gives you 2 plus or minus, and I'm going to figure out what this margin of error is over here. So we have 0.1 over the square root of 32, and then we're multiplying that by 2, and we get 0.0354. And so that is our margin of error. And And then what we're going to do is we're both going to add that margin of error to 2 and then subtract that margin of error from 2, and that's going to give us our interval. So that puts us about from 1.96 to 2.04. I did some rounding there. And we could then, sorry guys, I didn't slide that paper up well enough. And we can then get our interpretation of this interval, which says here we are about 95% confident that the mean weight of all small bags of this candy is between 1.96 and 2.04 ounces. Okay, and the reason I threw in this we are about 95% confident is this is a close approximation. I'm just trying to give you the basic idea of a confidence interval. Again, based on that empirical rule, that's that 68, 95, 99, 7 rule. We know that this percentage really, if you go to 2 and -2 deviations above and below the mean, is really 95.44% of the area. So it's not quite perfectly a 95% confidence level, but it's close. And we're gonna look, now that we've got the basic idea, in the next example, we'll look at the technical formula that's gonna get us a little bit more precise.